Okay, let's get started here. So we are able to execute the XTurb code in a Windows command prompt. Now let's go back to the manual. Here's the title page of the XTurb PSU users guide. And before we start opening an input file, let me make a few comments on what kind of input modules we have in the input file. We have a blade input list that contains all the geometric definitions, an operation input list where you can execute the code in 3 different modes. I call one the design, one the analysis, and one the prediction mode. The solver input list has solver and grid selections. The HVM input list concerns a helicoidal vortex method. We will learn more about that one in lesson 6 of this course. And BEMT is the blade element momentum theory, essentially what we have learned in lesson 2. Output files, they are general ones and there are method specific ones, meaning if you're using the vortex method, there will be output file specific to that. Okay, let's first start with the blade input list. And here are just a few more comments. If you would also like to run the XTurb code in a Unix environment, I can provide you with a tar file and you can do some things there. You can use the nohub command, and in general I like to use Cygwin. Actually I programmed the code within the Cygwin environment. That's also freely available on the web if you prefer that. Okay, here's again structure of the input file. So we first start with the blade input list. Let me open an input file. I go back to the Explorer, go into the NREL Phase 6 folder, right click the file, I open it with a program that's installed here. I like using Notepad actually, and here I am. I have an input file. I can scroll down and there's a number of parameters in there that we have to talk about. Okay, here we are. You can see here in the input file that the list is designated by the first line, and then further down there is an end to this first input list before the following input list operation starts. So we are talking now first what's here in the blade input list. First input parameter is the name of your input file or the name of your simulation. We're dealing with the NREL Phase 6 rotor, so that's a useful name. If you make modifications to your input files and save it under a different name, I also encourage you to change the name of the file, because this string here that contains the name will be printed into every single output file that the code gives you. So you can say NREL Phase 6 variation 5 version 2, however you want to call it. Second parameter is the blade number. Yes, indeed, the NREL Phase 6 rotor is a 2-bladed rotor, and we can see that here. Third parameter is the location of the root as a fraction of the radius. The NREL Phase 6 rotor starts with the first airfoil section located at 25% of the blade span or radius. This is what this parameter is telling us. Next parameter is called a taper definition. taper meaning actually the chord distribution. So with this first integer, we specify that there are two stations where we want to specify the chord. First one, and this is important, is always equal to the root location. And the last one is always equal to the tip location. But you can have as many as you like in between. Nice thing about the NREL Phase 6 rotor blade is that it has a linear taper, and what the XTurb code does is it only requires in such a case two definitions of the airfoil chord or taper, again in terms of the blade radius. Okay, so that means 14% chord at the root, which is at the 25% location, and about half of that, 7%, at the tip. And what the code does, it simply linearly interpolates all the other stations where you will have blade elements later. Let's say you have at the 30, 40, 50, 60, 70, 80, and 90% station further blade elements. So the code automatically linearly interpolates in between there. That's quite useful, and it makes it very easy to define geometric specifications. I go to the next side here, and now we specify the blade twist. And guess what? The twist distribution of the NREL Phase 6 rotor is everything but linear, and we're using here a total number of 20 locations along the blade to specify the twist. So N20, and then we have the R twist location, the radial location along the blade, and then the twist angles in degree. Again, first location in the respective R vector is equal to the root. That's important. The last one equal to the tip. And so we can define all the twist angles in here. Note that the blade root is twisted, in this case here, 20 degrees into the wind, while the tip is actually negative 1.81 degrees or 82 degrees out of the wind. Another nice thing about the NREL Phase 6 rotor is that it only has one airfoil all along the span, and we're using here in the sample input file one airfoil, so our airfoil is again equal to the root location, 25%, and this is the path to the airfoil data file. A // means that it's in the same directory as the input file is, and that's the name of the file. So we have it actually here in the NREL 6 folder. Here it is. You can have more than one airfoil along the blade span. What we have here in this sample users manual is at the 25% location we have the polar for a Reynolds number of 600,000, and at the breakpoint at mid blade at 50% there is another polar file that we read here. You will see for the PSU 2.5 megawatt turbine there are actually 6 to 8 different airfoils along the blade span. Okay, so that's what we have. Then we have blade sweep. You can specify that. However, in the current version of the code, it doesn't do anything. It's not being used. This is an example of an airfoil input file. It's based on an Xfoil input file, but it doesn't mean that the airfoil data you use with the XTurb code necessarily have to be generated with Xfoil. You can put wind tunnel data in here. The first 12 or 13 lines are just strings that the code ignores, so that's just the Xfoil file convention, and then it's interested in the first 3 columns of the input file only. The angle of attack, the lift coefficient, and the drag coefficient. That's all that it reads, that it mainly uses. It also reads the pressure drag coefficient in the 4th column, but the remaining column are being ignored. So if you have wind tunnel data available, you can replace the first 3 columns typically, and you can put the other ones to 0. It doesn't matter. And we can also specify dihedral, denoted by N dihed here, but this is also a feature that's currently not being used in the code, so we don't have to talk much about it. There's pix axis definition, and you can do that as well. Sometimes the pitch axis differs from the aerodynamic center of the airfoils, and so this is also something that's currently not being used in the code. So there's some more information about this here. So with that, that includes sort of the definition of the blade input list. So important things we have talked about is the name, the blade number, the root location, chord or taper distribution, and twist distribution, and different airfoils along the blade. I think a nice feature of the XTurb code is that different from other blade element momentum theory codes, where you have to specify each location of the blade element, and then you have to manually interpolate what's the chord and what's the twist at that element location. The XTurb code actually allows you to specify chord, twist, and airfoils and their respective distributions in different arrays, and whichever computational grid and distribution of blade elements or lifting line points is chosen later, the code automatically interpolates the input to the used computational grid. Okay, so this concludes the discussion of the blade input list, and we will then go ahead with the operation input list.